Hello and welcome to this video on understanding energy management to become certified and qualified energy manager. In this video, we will solve together several examples and problems related to electrical systems. So let's get started. Here we have our problem, a single phase 220 volt electrical loads draws 5 kilowatt and 27 amperes. What is operating power factor? A, B, C, D, or E? The power factor of an electrical load is a measure of how effectively electrical power is being used. In an AC circuit, the power supply can be thought of as having two components. Real power, measured in kilowatts, which does useful work, and reactive power, measured in kilovolt amperes, reactive kVAR, which is necessary for the operation of devices like motors and transformers, but does not do work. The apparent power, measured in kilovolt amperes, kVA, is the total power supplied to the circuit, which is the vector sum of real and reactive power. So the power factor is defined as the ratio of real power to apparent power, and it can be represented as the cosine of the phase angle theta between the voltage and current in an AC circuit. So for a single phase AC circuit, the apparent power kVA can be calculated by using the voltage and current by following the equation. The kVA, it will equal the voltage multiplied by the current divided by 1000. So in this problem, we are given the real power, which is 5 kilowatt. We also have the voltage, 220 volt, and we have the current 27 ampere. So we will first need to calculate the apparent power by multiplying the voltage by the ampere, and we will have the apparent power. And we can now calculate the operating power factor, which will be 84.17 or 84%. So the correct answer is D. Now we will look into another example. A utility penalizes customers for every kVAR in excess of 75% of the real power load. The minimum power factor that will entail no penalty is A, B, C, or D. Okay, so in order to determine the minimum power factor that will not result in a penalty, we need to understand the relationship between the real power, reactive power, and the power factor. These quantities can be represented by a right-angled triangle, known as the power triangle. In this triangle, the horizontal side represents the real power, the vertical side represents the reactive power, and the hypotenuse represents the apparent power. The angle between the real power and the apparent power is the power factor angle denoted by theta. So the power factor is defined as the ratio of real power to apparent power, and it's also equal to the cosine of the power factor angle. From the power triangle, we can also see the relationship between the reactive power, real power, and the power factor angle as tan theta equal the reactive power divided by the real power. So here the utility penalizes customer for every kVAR in excess of 75% of the real power load. This means that to avoid a penalty, the amount of reactive power must be less than or equal to 75% of the real power. To find the minimum power factor that avoids a penalty, we have to consider the limiting case where the reactive power, or kVAR, is exactly 75% of the real power load. Now we can relate this to the power factor angle using the tangent relationship, where tan theta will equal the reactive power divided by the real power. And now we will substitute the limiting conditions into this equation, where tan theta is equal to 0.75. And to find the power factor cosine theta at this angle, we first need to find the angle theta by taking the arctangent of 0.75. When we calculate this value, we will find that theta is equal to 36.87. So now we can calculate the power factor by finding the cosine of this angle, which is cosine of 36.87. So the power factor will be 80. So the minimum power factor that will entail no penalty is 80%. It means if the power factor is below 80%, meaning that theta is larger than the degree of 36.87, the ratio of kVAR, or reactive power, to the real power will be greater than 0.75, and this will result in a penalty for the organization. And now we will discuss the third and last example of today's lecture. An electrical system consists of 40 kilowatt purely resistive load in parallel with a 60 kilowatt partially resistive load with a power factor of 80%. And here the question is, how many kVARs of capacitance are required to correct the power factor of the total load up to 95%, A, B, C, D, or E. So now we have discussed in AC circuits, power can be categorized into real power, which performs the useful work, and reactive power, which is needed to establish magnetic fields in inductive components, but does not perform net work. Apparent power, which is the total supply and is the vector sum of real and reactive power. So the power factor is the ratio of real power to apparent power, and it indicates how effectively the supplied power is. As we discussed previously, a lower power factor means a larger portion of apparent power is reactive, leading to higher current and potential penalties from utilities. Adding capacitance to a system with inductive loads helps to counteract the reactive power, thereby improving the power factor. In this example, we will start by calculating the reactive power of the partially resistive load. Here we have the second load, which has a real power of 60 kilowatt and power factor of 80%. The relationship between the real power, apparent power, and power factor is the power factor is real power to the apparent power. And the relationship between real power, reactive power, and apparent power is the apparent power is the sum of the real power and reactive power. So from this, we can conclude the kVAR equals the real power multiplied by the tan arcus the power factor. And in order to estimate the reactive power, we first need to find the angle whose cosine is 0.8 or arcus 0.8, and it will be 36.87. To find the tangent of this angle, it will be the tan of 36.87. It will be 0.75. So the reactive power here is real power, which is 60 multiplied by 0.75, which is 45 kVAR. Then we will calculate the total real power of the total combined load. And here the purely resistive load has a real power of 40 kilowatt, and the second load is 60 kilowatt. So the real total power is 40 plus 60, which equals to 100 kilowatt. Then we will calculate the initial total reactive power for the combined load. The purely resistive load has a zero reactive power, and the second load, as we calculated right now, has a reactive power of 45 kVAR. So the kVAR initial equals 0 plus 45 will be 45 kVAR. And then we need to determine the target total reactive power for a power factor target of 95%. The total real power remains 100 kilowatt. And we need to estimate the total target, which equals the kVAR total target, which equals the real total power multiplied by the 10 arcus, the power factor of the target, which is 95%. So the kVAR total target will equal the real total power, 100 kilowatt, multiplied by the 10 arcus 0.95. Again, we need to find the angle whose cosine is 0.95, and it will be 19.80. Then we will find the tangent of this angle, which is 0.3287. And in this case, the kVAR total target will be the 100, the total real power, multiplied by 0.32, and it will give us the kVAR here is 32.87 kVAR. Finally, we need to calculate the required capacitance, and the required capacitance is the difference between the initial total reactive power and the target total reactive power. The capacitance will equal to the total initial, which is 45 kVAR, multiplied by the target, which is 12.13 kVAR. So the final answer of the required capacitance that we need, right, is 12.70. So today in this video, we have discussed the real, reactive, and apparent power, and the significant role power factor corrections plays in energy efficiency. And we discussed how better power factor means better energy use. And if you found this video valuable, please like it and share it with your network interested in energy efficiency and management, and subscribe for future content. Thank you.